Okay. Good morning, everyone. Welcome back to our class here. Can you guys hear me? Is the sound clear?
Yes, doctor.
All right. Yeah. Thank you, Ahmed. Yeah, I think we are ready to begin our class today. This is first of all just a very quick reminder about our lecture last time. What did we talk about last time? We actually we discussed the equations inside the BN junctions, and also we further discussed what needs to be changed for these equations if we incorporate them into a operational solar cells. Okay, if you remember, for the equations specifically, we have to introduce several new parameters. Specifically, that is going to be the generation rate, which is related to the absorption coefficient we mentioned before, as well as the recombination rate. Okay, for the recombination rate, we also introduce several parameters such as the carrier lifetime, as well as the diffusion length. Okay, and then based on the diffusion length, the carrier lifetime, we also look at the different scenarios that can happen inside a silicon solar cell. Okay, so if you remember the four different incident scenarios that we examined last time. Okay, depending on the location of the absorption of the excitation, these actually photons will have very different outcomes depending actually very specifically on the diffusion length. Okay, so remember in the top layer or in the top N plus emitter, for the first case, actually in this region you have a very, very short diffusion length. So immediately the generated electron and hole pairs, immediately they will be recombined. So we actually from this region, we do not expect too much of a current generation from this point. Okay, and then we mentioned the very ideal case, that is the second case, the second photon incidence, which happens inside the space charge region. So immediately the generated electron and hole pairs, they will be separated. Even actually you do not need to consider the diffusion process. Okay, and then a more common occurrence is the third scenario, where the electron and hole pairs they were generated, but it is beyond the space charge region. So from this point on, they need to diffuse first of all to the space charge region in order to be separated. But this requires that the distance from their absorption is within the diffusion length of the material that we are talking about here. Okay, so the conclusion is that if they are generated, roughly speaking, in the region here, then they can be they still can be harvested. They still can be transformed into electricity. Okay, but then we have the last case, which most of the time the electron and hole pairs, they cannot make it back to the space charge region because they are far away. They are longer compared to the diffusion length. In those cases, most of the time we do not expect too much actually generation from this scenario. Okay, so these are actually the possible outcomes actually inside a typical solar cell, which actually brings us back to the initial discussion. Okay, back to the earlier discussion where we look at actually the different processes we have inside a typical solar cell. Okay, so remember, typically we started from here, the absorption, and for that, we talk about how we can calculate the absorption efficiency. I think in the very beginning. Okay, and then there is the excitation process, which also depends on a certain excitation efficiency. There is the drift or the diffusion process. Typically is the diffusion. Okay, so there is a certain diffusion process here. Obviously, this depends on the diffusion length. And there is the separation efficiency, because under the electric field, it's not guaranteed that you can separate them successfully. Okay, and finally, as we said, there is also the collection process, because after the separation, they still need to reach the positive and the negative electrodes. Okay, so all of these processes actually, they are, each of them, they are very, they're equally important actually to the overall performance from the solar cells. Okay, which is why actually in the very beginning we were saying that we would like to come up with a certain efficiency, an overall efficiency or a total efficiency that covers actually all these process. Okay, and that at that time we were saying that this total efficiency we would like to define this as a sort of a quantum efficiency. Okay, a quantum efficiency. Quantum means that you are talking about numbers. Okay, you are talking about numbers. So this total efficiency, is telling you that the probability that you can convert one photon, okay, into one electron and hole pair. Okay, one electron and hole pair. And how likely is that? Okay. That is essentially the idea for quantum efficiency here. And if we go along with this definition, actually, this is where we have our parameter here today. We would like to define actually the so-called external quantum efficiency. Okay, external quantum efficiency. You will see that in papers sometimes they call this actually the EQE. Okay, the EQE, which is exactly the external quantum efficiency. And to denote that this is the external case, sometimes they will write that the efficiency, but it is with the external subscription. Okay, subscript here. But essentially, these two are the same. They're talking about for both of them. They are essentially our efficiency total when we started to talk about actually the process in this chapter. Okay, so what is the exact definition for external quantum efficiency? Again, we're talking about the quantum sense, so we need to look at the numbers. Okay, the number of particles, the number of photons. So specifically, the external quantum efficiency is by using the number of collective electron and hole pairs, right? Essentially, this is the number of charges that you can collect from the solar cell, divided by the number of incident photons. Okay, so obviously the ideal case, if you have 100% quantum efficiency, what does it mean? It means that you are doing one-to-one conversion. This is the best case scenario for the solar cell. Okay, you will be able to convert from one photon to one electron and hole pair, and later you are able to separate it, and finally they become free carriers, and they will be collected by the external electrodes, and they can go through the circuit. Okay, so this is the best case. Typically you cannot do better than 100%. And even for 100%, it's actually very difficult to achieve in solar cells. Okay, but this is typically the theoretical limit. Okay, the theoretical limit. And with this definition, now we can actually have a sort of a parameter that will give us the overall conversion performance of the solar cell. Okay, so the number of electron and hole pairs, typically we call this the capital N EHP. EHP stands for electron and hole pair, and this will be the number of photons. Okay, this will be the number of photons. And typically, obviously, from the definition, we need to define that these numbers, the electron and hole pairs, the number of incident photons, they happen within the same duration of time. Okay, within the same duration of time. So it is more common for you, instead of doing the counting of a total number of electron and hole pairs, total number of photons, actually you try to do a rate, of the numbers. Okay, so typically you instead of the number here, you want to write the number of electron and hole pairs per second, the number of photons per second, because typically what we have is actually related to the flux. You have the photon flux, you have the electron and hole pairs flux, and essentially they're talking about the rate of flow for these particles. Okay, so that is our definition for the quantum efficiency here. And I would like to emphasize on the word external here. Okay, because later we're going to have a very similar definition for another parameter that is not external, but it's also called another kind of a quantum efficiency. So the word external here means that you look at the solar cell from outside. Okay, you look at the solar cell from the external sense. Okay, so in this case, the solar cell basically is a black box. Okay, it's a black box. So the input obviously is the number of photons. So a certain number of photons goes in, and then a certain number of electron and hole pairs comes out. So basically, we do not care what's happening inside in detail. We just want to see what is the ratio of conversion from photons to electron and hole pairs. Okay, so that's why we call this efficiency the external quantum efficiency. Okay, so in the same line, we can also define another efficiency that is called the internal quantum efficiency. Okay, internal quantum efficiency. For the internal quantum efficiency, actually, it doesn't look at the overall solar cell as a black box. Instead, it will try to focus mainly on the electrical process. Okay, because as you can see, for all these processes that we plotted here, the first process, the absorption process, is actually related to the optical property of the solar cell. Okay, but starting from this point, after this point, the rest of the process is mainly related to electrical process only. Okay, electrical process only. So we have the excitation, which is talking about an electrical process, diffusion process, that is the electrical process, separation electrical, and collection is also electrical. Okay, so we already mentioned that the external quantum efficiency covers all the process, but what about the electrical process, right? If we just want to know the pure electrical performance of our solar cell, in this case, can we find another quantum efficiency that talks about this performance? Okay, so for the definition, the internal quantum efficiency is defined again very similarly, that as the number of electron and hole pairs, so that is our NEHP. Okay, but divided not by the incident photons. Instead, it's going to be divided by the absorbed photons. Okay, absorbed photons, which is actually which is talking about the number of photons after the absorption. Okay, how many photons can actually be absorbed? So if you look at the overall process, the total efficiency obviously is our external quantum efficiency, and because we have two process, or two procedures actually in this graph. So the first process is the absorption efficiency, okay, and then the second process is our internal quantum efficiency. So specifically, what is the relationship between external and internal? These two are very similar definitions, but essentially, the missing component is the absorption efficiency. Okay, so if you have the absorption efficiency, which we can find actually using our knowledge from before, in the chapter before, we just learned about how to calculate absorption efficiency, with the material absorption coefficient, with the material thickness, and then we can actually calculate the absorption efficiency, right? And then from here, whenever you have the external quantum efficiency, using the absorption efficiency, you can find the internal quantum efficiency. That will give you a pure electrical indicator. Okay, that will give you a pure electrical performance indicator. Okay, which is essentially what we are writing here. The internal quantum efficiency. If you want to calculate it, you can use the external divided by the absorption efficiency. Okay, and we said before that the absorption efficiency precisely it is our percentage absorption. And for percentage absorption, obviously, it will equal exactly 100% minus transmission minus reflection. Okay, so if you know already the transmission or if you know already the reflection, you can calculate from there. Otherwise, we have to use the other information, the absorption coefficient, as well as the material thickness and the reflection, etc. Okay, so with that, we will also be able to calculate the absorption efficiency. Okay, so this is the idea for the relationship between the two efficiencies that we have here. And this is actually these two concepts. I find that very often students will have some sort of a difficulty, to understand, the meaning from these two efficiencies. Okay, so feel free to let me know, if you have any sort of questions. Okay, as you can see also from the equations here, the absorption efficiency, it is less than 1. So you are taking an external efficiency divided by something less than 1. So this means that typically the internal efficiency, it will be higher than the external. Okay, it will be larger or equal than the external. So that is the typical case. Okay, do we have any questions, guys?
Doctor?
Yes, Omar, go ahead.
Can we reach an external quantum efficiency or an internal quantum efficiency equal to 100% for a specific wavelength if we optimize the whole solar panel parameters specifically for this wavelength?
Yeah, that is a very good question. Actually, we can. If you look into papers for some solar cells at the certain wavelengths, it is possible for you to reach 100% both internal and external quantum efficiency. Well, in that case, if you have if they are the same, essentially this means that you have 100% absorption efficiency. This is possible for certain wavelengths, and if at that wavelength you have the perfect electrical performance, yes, it's possible. Actually, it's you can see this behavior in from several solar cell designs. Okay. This actually question reminds me that we wrote that in the slide, but I forgot to mention this, that both the external and internal quantum efficiency, they are wavelength dependent. Okay, they are wavelength dependent. So you cannot just say that this solar cell has always a 60% quantum efficiency. Usually it's not the constant. Okay, you can only say that this solar cell has maybe 60% quantum efficiency at this wavelength, but at other wavelengths, we are expecting the quantum efficiency will change. We are expecting the quantum efficiency to always be a function of the wavelength. Okay, and this is different from the energy efficiency, definitely, because typically for the energy efficiency, we're talking about the energetic efficiency under AMS 1.5 spectrum. But for the quantum efficiency, it's not always a single, it's actually not a single number. Always you need to plot actually the EQE or IQE versus the wavelength. Okay, so that is something I wanted to add here on top of Omar's question. All right, any other questions, ladies and gentlemen? Okay, okay. So moving on, moving on to from here. So we talk about already the the natures or the essential idea for the EQE and the IQE, external and internal. Okay, so basically EQE is the total efficiency, is the total quantum efficiency we find from all the process in solar cells. So this means that this efficiency represents the overall combined optical and electrical efficiency. Okay, while at the same time the internal is a pure electrical indicator. Okay, since actually from the definition you can see that we are not concerned with the absorption. We just want to divide by the absorbed number of photons, and in this case we ignore completely the absorption behavior. Okay, and the missing link between them is the absorption efficiency. Okay, so as we said, typically the internal quantum efficiency is always going to be larger or equal than the external quantum efficiency, which you can actually see from here. This is the quantum efficiency plot for a typical, I believe, a silicon solar cell, because you see that the ending of the quantum efficiency is around the same bandgap wavelength for silicon. Okay, and obviously the highest curve is the internal quantum efficiency, because this is always the highest quantum efficiency compared to the external, and the external, it is always lower. Okay, and you can see that actually even for this example, at around this wavelength, you can actually have both 100% internal and external quantum efficiency. And for internal, you can see it has a wider range. Even around this wide range of wavelengths, we have almost a perfect electrical performance. Okay. However, it's just that because if you look at the surface reflection around this part, we have a high reflection from the solar cell, and because of this, the absorption efficiency is less than 100%. Okay, and therefore the external quantum efficiency will be less than 100%. Okay, and you can see that at which wavelengths we are having the biggest difference between the internal and the external, specifically around this part. Okay, here we have a very high reflection losses. Okay, reflection losses, and because we have a very high reflection loss, so the absorption efficiency is going to decrease. Okay, and therefore, even though we have a 80+% internal quantum efficiency, but the external quantum efficiency is actually much lower. It's only it's actually here. It's only 30% or so. Okay, and you can see that the variation here corresponds actually very well with the optical phenomenon that we are seeing from here. So for solar cell, actually, typically we would like to measure the external quantum efficiency. Okay, to see that at which wavelengths our solar cell is performing actually very well, and at another wavelengths the solar cell is maybe performing poorly. And this is actually the region where we can have a sort of an improvement. If you want to improve your solar cell, we should work on the solar cell at which wavelengths, and the quantum efficiency plot will give you this idea. Okay. And at the same time, you can combine the quantum efficiency with the optical measurement. Optically, you can measure the reflection. You can measure if you have a transmission from your solar cell. And from there, you can calculate the absorption. And from there, you can see that if I need to increase my solar cell performance or my solar cell absorption, which wavelengths should we be, should we focus more? Okay. So this actual information is actually very useful if you want to improve your solar cell performance. And typically, this information, you cannot find that easily from the IV curve. The IV scan will not tell you this information. Okay, so that is the importance of having this wavelength sensitive data. You want to have this data so that how to improve the performance. So now this is a real example, right? A real example for the quantum efficiency. Now the question is, ideally speaking, what should be the ideal quantum efficiency? Okay, ideally, what should be our target? Okay, what should be the ultimate target for external quantum efficiency? We know that for any semiconductor, you're always going to have a certain band gap. You're always going to have a cutoff wavelength. Okay, so ideally speaking, obviously for any external quantum efficiency, you can never expect that the EQE will always be 100%. And without any termination. Actually, because of the band gap, we expect that at the band gap wavelengths, okay, always we would like actually the quantum efficiency to remain 100%, but suddenly it's going to come down to 0%, and then from there it's always going to be 0% onward. The reason for this is that if you go beyond the band gap, obviously you cannot have any absorption, okay, because beyond the band gap, the absorption efficiency is going to be 0%, and with that, with that said, obviously the external quantum efficiency automatically will have to be 0%. Okay, but within the band gap, we hope that ideally speaking, obviously the best quantum efficiency should be 100%. So ideally speaking, we're talking about a rectangular profile. Okay, we're talking about a rectangular profile. But as you can see from the previous slide and also from the slide here, for the real case, actually it's very far away from a rectangular shape, from a rectangular profile. Okay, so what's causing the difference here? The real quantum efficiency typically will suffer at the short wavelengths and at the long wavelengths. Okay, so let's look at the case, from the beginning, from the left side and from the right side to see what's causing the reduction or the deviation here. Okay, so at the short wavelengths or at the blue light, right? Blue light has a typically very small penetration depths because they have a high energy. So very, very easily they will be absorbed by the semiconductor. Okay, because we also discussed actually previously using actually the absorption coefficient and the penetration depths. Okay, you can see that as we increase the photon energy, if we go to the blue portion of the photons, typically absorption coefficient is very high, and the penetration depth here is actually very low. So most of them, they will be absorbed near the front surface. Okay, but then we just said earlier, actually today and from last lecture, near the front surface, near the emitter. Typically here, you have a very high recombination, okay? The diffusion length will be very short, and near the surface, also you have the surface recombination. So the blue portion that is being absorbed near the front surface, very quickly they will be recombined. And if they are recombined, then in this case, this actually will cause the reduction of external quantum efficiency. Okay, so ideally we are hoping for a rectangular shape quantum efficiency, but most of the time the external quantum efficiency will start from very low because you have a very high losses from the short wavelengths photons. Okay, and then what is the problem at the long wavelengths? At the long wavelengths, you can see that actually we're talking about cases actually in here or near here. Okay, in this case, they have a very high penetration depth. Okay, so these photons, they will be, most of the time, they will be absorbed very deep into the solar cell. But if it's a very deep into the solar cell, it means that typically they will be absorbed near the backside of the solar cell. Okay, near the backside of the solar cell. So if you are too close to the backside, the problem again is that you have a high surface recombination from the backside. Okay, so they can easily be recombined. And also near the back surface, typically this is very far away from the space charge region of the solar cell itself. So remember that you have to also overcome the diffusion length. Okay, you have to consider the diffusion length. If it's longer than the diffusion length, the distance, then in this case you have a very high chance of losing the electron and hole pairs here. Okay, so also in this case, near the band gap, we also expect that the practical or the real absorption, the quantum efficiency, is going to drop. Okay, so finally, if we look at the real absorption, the quantum efficiency, typically it shows a profile like this, right? You have a plateau in the middle, but then in the beginning and in the end, actually you have a declining quantum efficiency. Okay. And even in the middle plateau, actually you may expect some sort of deviation or reduction from 100%. For one thing, the reflection is difficult for you to reduce the reflection to 0%. This is not always possible. Okay. And second thing, we always expect typically some sort of recombination losses, some sort of some other electrical losses. So all of this. This will reduce the overall quantum efficiency. Okay, but if you really optimize your solar cell, like we said, at a certain wavelength, at a certain point, you can achieve 100% external quantum efficiency. And actually, for a very efficient solar cell, internal quantum efficiency is actually typically very good. They will show almost 100% internal quantum efficiency. But remember, for external quantum efficiency, it's more difficult to achieve 100%. Okay, although it's possible at a certain wavelength. So this is actually something you can think about when you design your solar cell. Okay.
Doctor?
Yes, Omar, go ahead.
Why don't we have the diffusion length problems in the blue, which is the short wavelength, even though we have it for the long wavelength?
In the blue, we also have the diffusion length. This is actually for the emitter case. We talked about last time. That is this one, right? That is the first case here, right? We said that actually the diffusion length here is actually very, very short. It's almost a 0. So again, it's the same thing here. Near the front surface, actually in the emitter, first of all, it's very close to the front surface. So it's very easy to be combined, to be recombined by the surface recombination. Second thing, here you have a high doping density. So you have a very small diffusion length. So even if it's escaping from the front surface, it cannot travel very far in the emitter. So again, it's going to get recombined very quickly. So it depends actually heavily on the diffusion length here. Okay?
Yeah, okay.
Okay, so I think the last question I would like to present to you for the quantum efficiency, it is something we actually, I think maybe some of you asked me before. So if we have, for at a certain wavelength, if we have 100% external quantum efficiency, does this equal 100% energetic efficiency? Okay, so essentially we're asking what is the relation between, let's say, external quantum efficiency, okay, versus the typical energetic efficiency we talked about, before in other courses as well. Okay, what is the relation between the two? Okay, what is the relation between the two?
Doctor, I think the external quantum efficiency is a kind of representation of the current. So we have another factors like the VOC, the open circuit voltage, and the fill factor. These will affect the overall efficiency, the actual efficiency.
Exactly,
so
yeah.
It's a kind of a relationship between the two.
Yeah, very good, very good. So for that, basically we have to think about, the solar cell or the solar PV, device. Basically, we have to look at this as a black box, okay, as a black box. So for these two efficiencies, basically we're talking about the same phenomenon or the same process, but then we're looking at things from different perspectives. Okay, what I'm saying here is that you have inputs, you have outputs, but then the inputs and the outputs you can use different parameters to evaluate them. Okay, so for the quantum efficiency sense, we are saying basically the inputs that are the number of photons. Okay, are the number of photons, or if you want to make it general, you can say that the number of photons per second. Okay, number of photons per second. So per second, how many photons we have incident on the solar cell? Okay, on the solar cell. And at the output, what do we have? As Omar was saying, typically it's very easy for us to measure the current coming from the solar cell. Okay, for quantum efficiency, typically we refer to the maximum current, that is the short circuit from the solar cell. Okay, what is the purpose of the current here? If we take the current, which is the charge per second, divided by Q, okay, essentially we have actually the number of charges, okay, per second, okay, the number of charges per second. So we know that from the physical point of view, if you have a perfect solar cell, then the ratio should always be 1 versus 1. Okay, for one incident photon per second, you should be able to convert it to 1 electron and hole pair. That is the best case scenario for the solar cell device. Okay, but what about the energy efficiency? Okay, what about the energy efficiency? Typically for the energy efficiency, we were using actually the irradiance. Okay, we are using the irradiance, and then from the solar cell, we are measuring actually the power. Okay, the electrical power from the solar cell. And specifically, we know that the maximum power equals I short circuit times E open circuit times fill factor. Okay, times a fill factor. What about irradiance? If you think about irradiance is actually watt per square meter, and watt per square meter. Essentially, it is if you want to find the correlation between these two, what do we need to do? We have the number of photons. Okay, but how much energy that is contained within this number of photons? For that, we have to use the photon energy. Okay, so if we assume that this is a single wavelength photon, then the photon energy for one photon will equal Planck constant times the speed of light divided by its lambda. Okay, so if we take this photon energy times the number of photons per second, essentially we have energy per second. So this automatically will translate into a watt unit. Okay, into a watt unit. And if we are talking about number of photon per square meter per second, then automatically this will become the irradiance. Okay, this will become the irradiance. So from the input side, if you want to calculate, if you want to go from external quantum efficiency to the energetic efficiency, the missing link is that you need to know the energy per photon, especially the wavelengths of the photon. Okay, and from there you can calculate the corresponding irradiance that is coming from this number of a photon per second. Okay, and then from the output side, actually the missing link is just the potential and the field factor. We need to know that the how much potential that is contained from the charges that we are getting. That how much is the voltage difference we are getting from both sides of the solar cell. Okay, and then also consider field factor, but typically the potential, that is the more important factor here. Okay, so for that, actually, for that, you also have to consider a couple of things we mentioned before, because now we involve actually the potential here. So with the potential involved, if you want to know the difference between the photon energy with the electrical power output, remember that we also have to think about the band gap structure of the solar cell or of the semiconductor. Okay, because specifically we said that for some cases, for some wavelengths, if the photon energy is too high compared to the band gap energy, in those cases, actually you will be losing part of the photon energy. So this means that for the energetic efficiency, part of actually the incoming irradiance or part of the incoming photon energy, it will be lost automatically compared to the band gap. And therefore, if you compare against the potential you get actually from the solar cell or from the semiconductor here, you will be losing some of the energy. But this will not reflect actually for this process. It's not going to reflect in the quantum efficiency. Okay, because if you have the ideal conversion here, for this case, the quantum efficiency, it is still 100%. Okay, if you can do 1 versus 1, we consider this quantum efficiency to be 100%. And if you have 100% quantum efficiency here, actually you can roughly calculate the energy efficiency. Okay, how much is the energy efficiency we have in this case? Well, roughly speaking, this is the energy loss. This is the energy gain. Okay, so roughly speaking, when we have 100% quantum efficiency here, roughly speaking, for this case, the energetic efficiency, right? It is actually around 50%. Okay, it is around 50%. So with this example, I just want to show to you that actually the external quantum efficiency and the energetic efficiency, they are related to each other. If you have the other information, you can actually convert the external to energetic. There is the possibility, but at the same time, you cannot equate them always. Okay, they do not equate automatically. Because usually they have a big difference between them, right? Because of the thermalization losses, that we mentioned before. That is one thing. Okay, so this is actually I think that one of the main conclusions actually I want you to remember actually from the lecture here. Okay, all right. So so this is actually what we discussed actually in solar PV, regarding the thermalization losses. Okay, so in the end, you have to consider these big thermalization losses here, because they are very significant. Okay, and they actually will give you actually different energetic efficiency compared to the quantum efficiency. Okay, all right. So with that said, I just want to, as the last part, to introduce another parameter that you also find very often in papers, but at the same time, this parameter is directly related also to the quantum efficiency. Okay, so trust me, this parameter is not difficult if you understand the quantum efficiency. So this parameter, it is also a function of the wavelengths. Okay, that is called the spectrum sensitivity. So basically, if we look at the solar cell as a photodetector, okay, we would like to know how much current we can generate from the photodetector versus a particular, incident optical power. Okay, so specifically for the spectral sensitivity, we define the sensitivity as the photocurrent, right, at this wavelength divided by the optical power from the incident photons. Okay, so this is actually more similar to the energetic efficiency that we just mentioned, because here you have current and you have the optical power. and it's very easy for you to convert the optical power into irradiance. Okay, because essentially, they are very similar to each other. So this is just another way to look at the quantum efficiency, but from the current and the power perspective. Okay, and in fact, the sensitivity is directly related to the quantum efficiency. Okay, because if you think about it, the photocurrent equals charge per second. Okay, charge per second, and obviously the optical power, is equals energy per second. Okay, energy per second. So charge per second, as we said, is essentially the number of electron and hole pair. By the way, this is per second. Okay, times q, and the energy from the photon is energy per second from the photon is essentially the number of photon per second, right? Times the energy of the photon here, because essentially we need to we're talking about the photon energy. Okay, so if you substitute actually this into that, this part automatically becomes our external quantum efficiency. Okay, and the remaining part they're constant, just except for the wavelengths. Okay, just for the wavelengths. So if you want to go from quantum efficiency to spectral sensitivity, then the only missing information is the wavelengths. Okay, is the wavelengths. You have to use the wavelengths and then times q divided by Planck constant times the speed of light. Remember that you have to match the units with the constants here. So in this equation here, after we calculate the constant, we change the constant into micrometer unit. Okay, so it means that if you want to calculate using the wavelengths here, you have to convert the wavelengths also into micrometer. Okay, so that they will cancel each other. And this ampere divided by watt is simply telling you the units of the spectrum sensitivity, because the spectrum sensitivity, it is a current divided by power. So if you use this constant as is written here, the value you get from here automatically will have the unit of watt ampere divided by watt. Okay, and then the quantum efficiency is just a unitless parameter, right? Because we're talking about a certain percentage without the units. Okay, so this is actually the spectrum sensitivity, very similar to the quantum efficiency. It's just that you have to combine also with the wavelength information. Okay, so it may seem a little bit complicated, but I hope that the next slide will give you I think a better explanation. So if I were to plot, right, spectrum sensitivity versus wavelengths, okay, and we would like to know what is the limit for spectrum sensitivity, because we know that the limit for quantum efficiency is 100%. Okay, so if we want to know the ultimate limit for spectrum sensitivity, right, we have spectrum sensitivity equals wavelengths divided by 1.24 micrometer, okay, and then times the quantum efficiency. But then we said that we would like to know that when the quantum efficiency is 100%, how do the spectrum sensitivity look like? Okay, actually, if you substitute 1 into here, this part is gone. Essentially, you have just lambda divided by 1.24 micrometer, which is a constant. Okay, and it is a linear function. Okay, it is a linear function. So which is why here this dashed line is indicating 100% external quantum efficiency. This is the maximum spectrum sensitivity you can hope to get. Okay, you can get, but then in reality, it's very difficult for you actually to approach this 100% external quantum efficiency. Typically, you can only do that at a certain wavelength. Okay, what about real solar cell? What about real device? Well, here it shows 2 examples for you. Okay, so these are the corresponding sensitivity for a standard solar cell and for a high performance solar cell. Okay, again, notice that in the beginning of the spectrum and in the end of the spectrum, we have this decrease because essentially, they are they need to account actually for the decrease in external quantum efficiency. At the short wavelengths, we have the recombination losses for the high energy photon, and near the bandgap, we also have recombination losses from the long wavelength photon near the backside of the solar cell. Okay, so both of this, they will contribute to the losses here. Now you might be wondering, if I have 100% quantum efficiency, so if we talk about, if we use the example from before, if the quantum efficiency, right, follows the ideal profile like this, okay, so how would this translate into a spectrum sensitivity? Well, it's going to show the linear variation, but precisely at the bandgap, it's going to come to 0%, okay, because starting from this point, the external quantum efficiency is 0, and therefore the spectrum sensitivity will also be suddenly 0 from this point on. Okay, so a triangular profile should be the ideal spectrum sensitivity. But other than that, you know, it's similar to our discussion from before. You know that the you are expecting some deviation from the long wavelengths and from the short wavelengths. Okay. So is this part clear, guys? Everything okay? All right. So that is actually the last part of the spectrum parameter that we would like to mention. Right? We talk about the external, the internal quantum efficiencies. We talk about the behavior of these guys. We also talk about the correlation between the energetic efficiency versus the quantum efficiency. And the last part we mentioned is just an additional discussion on the spectrum sensitivity. Okay, and then for these couple of slides, we would like to talk about the electrical models. Okay, what are the typical circuit models we can apply for a solar cell? Okay, so if you recall from the solar PV lecture, we started from the simplified model. Okay, we started from the simplified model. We have the one current source here to represent the generation of a photocurrent. So these are basically, this is related, remember, to our generation rate from the equation before. Okay, and then for the PN junction itself, we have this. We have actually a semiconductor diode here to represent the PN junction. Okay, and that is our simplified model, and this is the equation we have been using in solar PV. And we were also saying that in the semiconductor diode, typically we have to add the modification here. That is the ideality factor. Okay, ideality factor. This is to represent some phenomenon actually inside the PN junction. Okay, and then in solar PV, we were also saying that the simplified model sometimes is too simplified. It cannot represent all the electrical phenomena we are seeing. Typically, we may expect the electrical losses actually from the series resistance and from the shunt resistance. And therefore, we can add additionally 2 resistance into the circuit, and that is our standard model for understanding solar cell. Okay, and it will be represented by this equation here. Specifically, you can notice that there is a RS in the exponential term, so this will cause a decrease of the output voltage. Okay, and then in the current term, we have this additional negative term that is mainly representing the additional current loss. Okay, additional current loss, and both of them, they will lead to reduced performance actually from your solar cell. Okay, so that is the standard model we also talk about. So I believe that this is a familiar picture you saw from before. This is the simulation of changing the RS and R shunt using the standard model, or sometimes we call this the single diode model. Okay, so RS typically will try to reduce actually your I short circuit. Okay, at the same time, at the low current, you have almost the open circuit. Okay, but then for R shunt, it's doing the opposite. When you increase actually the voltage, right? Or actually you have almost the same I short circuit, but at the same time, at the high voltage, you will have more losses, and the V open circuit will drop significantly. Okay, so that is what you can see actually from the simulation here, and lastly, we would like to introduce a new model, right? That is more comprehensive, that is more complicated, but it can cover more effects happening inside the solar cell. Okay, So the problem with the previous simplified equation is that this equation actually assumes no recombination inside the space charge region. Because in the space charge region, remember, we also call the space charge region the depletion zone or depletion region, meaning that actually in this region, we are expecting zero free charges, okay? Zero free charges. And if it's a zero free charges, typically it means that the recombination will be very minimum because remember, if you want to recombine with something, you need the one electron, you need the one hole typically, right? But if you have a zero free charges here, it means that the chance for recombination is going to be very small, okay? But then recombination actually happens inside the spatial region. It's just that there is typically a relatively light effect, okay? So if you want to describe a more realistic device, eventually you have to somehow consider the recombination effect inside the spatial region, okay? And that is partially the reason why we introduced the identity factor, into the equation. But then, with the one identity factor, with the one Tau actually in the circuit, the problem is that it's not enough to describe fully the phenomenon that we are seeing. So this is where we come to the so-called 2-Tau model, okay, where we would like to actually model the current more precisely by actually 2 models of semiconductor Taus. And the thing is that each of them, they have a different identity factor with a different recombination behavior. Okay, so we will be using a Tau of an ideal Tau of identity factor equals 1, and then another Tau with the identity factor equals 2. Okay, and they are controlled specifically by the 2 saturation current here. So the ratio between the saturation current that will control which Tau is actually dominating in the circuit. Okay, so this is actually the equation for the 2-Tau model. Okay, for the 2-Tau model with the same RS and R shunt. It's just that we are attaching a new Tau model here with the different ratio to control actually the interaction between them. Okay, so that is the 2-Tau model we would like to actually mention here. Okay, so actually now I just want to go actually go to the software that we were using previously for solar PV. Okay, that is the PV Teach software. So if you allow me to go there, just 1 second. So it's currently not showing, I think, on my side. Okay, guys, sorry, I'm back. Can you hear me?
Yes.
Okay, yeah. Apologies. I think for whatever reason, I think my Microsoft team doesn't want to work with the software. But let me try again very quickly, see if it works or not. Hopefully, it will not crash again. Okay, so this is actually the software we were using with our textbook back in Solar PV. Actually, you can find all the models we talk about here today in this software. So if you're interested, just find this software and you can explore the different options that we have. Okay, so for instance, the first model is the simplified model. We can see the IV characteristic based on the parameter that we put in here. Okay, you can also do the power curve. Right? Of course, the scale is a little bit off, but the power curve is there. And then you have the other model, which is the effective model. But effective model essentially is just by adding a series resistance without the shunt resistance. Okay, and then more commonly we use the one-dial model where you have both the RS and R shunt, and you can define actually each parameters separately. Okay. And again, you can try to show the behavior from the one-dial model. You see that this curve is actually very flat, very linear, because we have a very large RS and a very small R shunt. So this is giving you very bad performance here. Okay, and finally we have the two-dial model. Okay, the two-dial model. You can see that we have a dial number 1. Okay, that you can define actually the dial factor, which is related to the ideality factor. The other one is the saturation current for the first dial, the saturation current for the second dial, and then the ideality factor related parameter to the second dial. Okay, so in this case, you can actually define a more complex solar cell model from here. Now, what can we do with this model? In the end, if you want to understand the behavior of your solar cell, you want to know, for instance, how much is the RS, how much is the R shunt inside, okay? And if you apply the two-dial model, we would like to know that how much is the ideality factor, we extract from there, okay? So actually with the PV teacher, with this simple software, you are able to do some parameter extraction. You can do fitting with your experimental data. Okay, so you can see here, besides plotting the behavior, besides plotting the IV characteristic from the model, we can also import, a certain measurement of our own. If you have your own measurement, you can actually import your data into here. And then what you can do next is that you can do fitting. Okay, you can try to use your model here to fit to the actual experimental measurement that you have, maybe a text file, maybe an Excel sheet, you can import into here. Okay, you can. I think this is not exactly English, but this button will let you import your measurement data, and then after that you can do the fitting. Right, if you set some initial parameters, from there you can do fitting, and these parameters will change after the fitting. So, and with a certain accuracy. And from there, it will tell you whether you have a very good fitting or maybe you have to improve your parameter setting, okay? Or maybe if you cannot get the good accuracy, you may need to find a more complex model. So this is actually the idea for the parameter extraction, okay? For the parameter extraction. And obviously, we have some simplification. If you want to just do simple parameter fitting, actually, we talk about this briefly in Solar PV. If you don't want to do the fitting, you can actually try to do approximation. Right? You can approximate the slope near the V open circuit. From there, you can find RS, and then you can approximate the slope near the I short circuit, where you can find R shunt. Okay. And then for the saturation current, what you can do is that you can follow actually this equation. You can do I short circuit times exponential minus the open circuit divided by VT. Okay. Can you guys still hear me?
Yes, Doctor.
Yes, we can.
Okay. I thought I'd lost the connection again, but yeah, okay. So this is what we can do. You can use the open circuit, I short circuit, and you can actually try to find the saturation current. But then this sometimes is difficult to do because typically the saturation current is a very small value. Okay, so it's very easy for you to end up with a very large error from there, because it can deviate easily by orders of difference. Okay, but then obviously the more accurate extraction should come from fitting, right? You should try to fit your IV data to a certain model that we just talked about. Using our software or using MATLAB, you can even ask MATLAB to fit to a customized equation. Okay, and then you can define how many parameters you would like to fit. So, but yeah, this is definitely doable, for the models. Okay, so so that is basically the electrical models. Typically we can apply for solar cells. Okay. Now, actually, near the end of this chapter, we would like to talk about some designs or some additional design approaches that we can apply for silicon solar cells specifically. Okay, so we talk about actually the same phenomenon before in solar PV, that if you want to reduce optical losses, okay, what can you do here, right? What can you do to reduce the optical losses? For that, actually, you can try the two approaches that we mentioned in solar PV. One is using the anti-reflection coating. Okay. The second approach is with the surface texturizing. Okay. So these two methods, we already talked about them, so there is no need to repeat them here. And then also we talk about the other method if you want to reduce additional optical losses. Okay. So we mentioned that the contacts near the front surface, this is typically a source of optical losses. Okay, this can cause some shading on the front surface, especially if the contact is higher compared to the silicon surface. So one of the methods to reduce this shading is by using the bury contact design. Okay, we can actually bury the contacts into the silicon surface. In this way, we have a minimum height above the silicon, so that the shading losses is going to be reduced. Okay. Now on to something new here. What else can we do, to increase the silicon solar cell performance? Okay. What can we do, to further increase the performance? One of the things we would like to introduce here is the so-called back surface field. Okay, back surface field. So what is the back surface field? So remember that we were saying that for the generated, electron and hole pairs, if they absorb and very deep into the solar cell, there is a certain risk here, that maybe they will contribute to a loss. That is near the back surface. Typically, this is where we have actually a very high surface recombination. Okay, with the very high surface recombination, basically the back surface is always attracting, the electron and the hole pairs. Okay, so they have a tendency to be attracted to the backside, but then if they reach the backside, they will be recombined, and this is something we do not want, in our solar cell. Okay, so what can we do to reduce actually the back surface recombination? The solution is that we would like to insert an additional layer here near the backside, right? This is the back contact. Okay, And the feature for this layer is that compared to the base layer, typically we're talking about a p-type, a typical p-type semiconductor. And for the back surface layer, where we would like to introduce a p+ doping layer. Okay, a p+ doping layer. So what does a p+ doping layer here accomplish? If you look at the energy band diagram, right, by inserting an additional layer here, we know that naturally, if you plot the electron energy, diagram from the p-n junction, there is typically a slope or a bending, from the p-n junction. Okay, a very big jump because we're using very different materials on both sides. We're talking about n+ to p. Okay, but then if you insert a p+ here, it's going to be very similar to a p-n junction, but the energy band bending will be much smaller. Okay, because here you have a higher doping density, you have a more free host. So initially you will have a free host diffusing from the p+ side to the p-type side, and then you can try to go through the similar, deviation or discussion process with the p-n junction. Okay, and then you'll realize that after inserting this p+ layer, what does it accomplish? Actually, it will introduce another small energy band bending near the backside. Okay, near the backside. So, how would this help us? Remember that if you have after the charge separation, typically we want the electron to go this way, right? While the hole to go the other direction. So this means that typically we would like actually the back surface to be accepting hosts, but at the same time we don't want the electron somehow to wander to this part. Okay, because if the electron comes to this part and they come out from here, essentially in terms of the current, you are using the electron current to cancel the whole current. So you are reducing actually the current from actually the overall solar cell. Okay, so if we inserted this additional layer here, we have another slight bending here. And with this slight bending, remember this scale is talking about the electron energy. Okay, electron energy. And with this uphill slope, electrons actually will have the tendency to be turned back in this part. Okay, so even if you have electrons wander into this part, they will be rejected by the back surface field. And in this way, you can reduce actually basically the charge carrier losses. Okay, you can reduce the losses, and because they're turned back, also you avoid the unwanted recombination at the backside. Okay, so this is the idea for the back surface, field layer that we're talking about here. Very similarly, if you are worried about the front surface recombination losses, very similarly, you can also add another front surface field layer, right? To basically to deter the host actually from this side. Okay, to deter the host from this side, to reject the host, so that most of the time you have just electrons coming out from this side without too much losses. Okay, but then for the front surface field, remember you have to insert a even heavier doping n++ layer. Okay, near the front surface. Okay, and then in the rest of the emitter, you still have the n+ emitter here. So this is the idea for the front surface field. Okay, well, this is for the back surface field. Okay, this is for the back surface field. And there is another advantage we would like to mention here, that if you look at the overall p-n junction, okay, the overall potential that is within the junction, it is actually increased. Okay, it is actually increased. It's increased even further by the back surface field difference here. So another slight advantage we get from using the back surface field is that the open circuit voltage from the solar cell actually will increase slightly. Okay, because across the p-n junction now, you have an even higher potential compared to before. So this is actually a very useful design for in solar cell that can reduce the recombination losses for you. At the same time, it's going to give you a slight performance enhancement. Okay, so that is the back surface field. Yeah, any questions?
So, Doctor, this is like we are increasing both the internal quantum efficiency and VOC at the same time, leading to an increase in the overall efficiency.
Yes, you can say that. I think, yeah, this will work for specific cases and for specific photon or carrier cases. Yeah, but definitely, in the most ideal case, yes, it's going to increase both efficiencies.
And doctor, for the doping, is it a simple procedure for both sides of the silicon cell, the N and P?
It's a very common practice actually in semiconductor processing, that yes, you can dope into the surface. I will not say that it's very easy to do, but it's a very common practice. Okay, and definitely if you want to introduce a back surface field, you have to control the doping level very precisely. So obviously this will add to the cost of the solar cell. Okay, yeah. But at the same time, practically in all, if you look at the papers for all the high performance solar cells, most of the time they will have a back surface field or front surface field. Okay, but of course at the sacrifice of cost.
Yeah, Doctor, is there a possibility for impurities from the contacts to propagate through the material and become traps?
And become what?
Traps for recombination.
Yeah, definitely. Actually, the diffusion of metal or impurities in the metal, they can actually go over or cross over into silicon, and then they become a problem actually for silicon solar cells. And actually, you can see also this phenomenon in actually later in other solar cells that we talk about. For instance, for those thin film solar cells, a very typical electrode. It is the so-called ITO, that is a transparent conductor. Okay, and this stands for indium tin oxide. And then you can search about it, but a very common concern for this ITO electrode is that the indium ions here, they have the tendency actually to diffuse into the solar cell layer. And then it's going to cause some unwanted phenomena inside the solar cell layer. So these things actually they can happen. Okay, and typically if you worry about this phenomenon, you do have to come up with some methods to prevent them. Okay, so yeah, it is a concern actually in solar cell. It's a very good observation.
Okay, thank you, Doctor.
No worries. So let's try to move on. So this is actually here is an example for the front surface field, okay, where we introduce actually the N++ layer very near to the electrode. And in this way, between this interface, you can also create energy banding or an electric field, if you like, that will basically repel the unwanted holes from the front side. Okay, so this is actually a very useful design if you want to learn more about actually solar cells. Lastly, we would like to mention today the surface passivation. We talked about this before earlier, that typically for any surface that you cut off suddenly, typically at this surface you have the dangling bonds, and these dangling bonds are the reason for high surface recombination rate. Okay, so these dangling bonds, they will be attracting electrons, they may be attracting holes, and whenever they capture electrons and holes, they will contribute directly to recombination losses. Okay, and typically they have a very high recombination rate, that they will recombine a lot of carriers. So what can we do to reduce actually these kind of surface recombination losses? One of the options we mentioned before is to close the open bonds. Okay, and this procedure is called a surface passivation process. A very typical closing method for silicon is that whenever you have these open silicon bonds, considering that you can oxidize the silicon very easily. So if you increase or if you heat up the silicon in air, the oxygen basically will come to the open bonds. Okay, and then they will be bonding with the open bonds here. And if they bonding with the open bonds here, this part will become neutral. So it's no longer attracting electrons or holes actually from this side. Okay, so passivation can be done by by converting the surface of silicon into silicon dioxide. So here's an example. We have the surface of texturizing that you are seeing here. We have the anti-reflection layer that's on top, but below the anti-reflection coating, we have a yellow layer here. That is the silicon dioxide. So this silicon dioxide layer, it is our surface of passivation layer. Okay, so in this way, you can reduce actually the recombination losses on the front side. And if you notice from the back side, we also have the passivation layer here. Okay, so that this will passivate the surface to reduce the backside surface recombination. Okay, and if you notice actually from the feature here, we also notice the back surface field layer, that is the P plus, and then we have the base layer. So between them, we have the back surface field. Okay, so these are things that you can notice actually from the design here. So maybe we'll leave I think the rest of the slides to next week. And I think if we finish by Tuesday next week, maybe on Thursday we'll try to do a small quiz on the first chapter. Okay, so I will announce on Blackboard or in the Microsoft Teams group about this. But I think in general the idea is that we will do an online quiz. Okay, maybe at the end of our lecture, so that you can. I think we'll do partially the lecture, and then for the rest of the time, you just log on to Blackboard and start the quiz. Okay. Is there any questions before we wrap up today?
Doctor, you brought up electrical models. Okay.
Yes.
Is there any model that accounts for stray capacitance and line inductance?
Those are, I think, in AC applications typically, right?
Yeah.
But for solar PV, typically most of the time, solar PV is considered as a device operating in the DC domain. So most of the time, I think the models that were involved typically they do not focus specifically on the AC domain. Okay, but this is a very interesting thought actually, because I recently came across a paper that is talking about the performance of solar cells or solar PV in the AC domain. So basically, they were studying if you have an AC signal light source, if the light source is on and off at a high frequency, what will be the performance from the solar PV? I think in that case, the capacitance, inductance, they become actually much more important.
Yeah, because even the normal light, it fluctuates, right?
Yeah, it fluctuates, but at the same time, the fluctuation compared to the DC light component, it is relatively minimum. Maybe you are talking about 5% or less than 10%, and also the fluctuation is not it's not regular. Meaning that yes, it's fluctuating, but it's not steady at the 50 hertz. So I think before most people didn't realize that to study this performance. But yes, actually the paper I saw is actually very recent. It's this year. They specifically studied this phenomenon. I think the paper, the topic of the paper is talking about is something like a AC solar PV or AC solar cell. You can search about this. It's actually very interesting to read.
Thank you, Doctor.
No problem. If there are no more questions, I think that's it for today. Thank you guys for attending our lecture here. And I think that's it for today. You can log off now and have a nice weekend, guys.
Thank you, Doctor.
No worries. Thank you.